In this example, we are considering the problem of finding the potential inside the unit circle when we know that the boundary conditions on this red part is different from the boundary condition on the remaining blue part of the circle. So it's 3000 here and minus 3000 on the lower part. So the problem is then to find the potential inside the circle. And it turns out that this transformation, this Möbius transformation, maps the interior of the circle to the right-hand side of the complex plane, which we call the UV plane, or the double U plane if you like. So we are going to utilize this conformal mapping to solve the problem, because we know the solution of this problem. In fact, previously we considered an example where we have a constant boundary condition here on this straight line and a constant boundary condition on that straight line, and the angle is alpha. Then we have the solution. We know that the complex potential is given by this expression. So we are able to solve the problem in the right hand side of the complex plane by taking the real part of this function. But no, exactly as before, we have to replace this set with W, because in this plane we are using the variable W, but in the original problem we use the variable set. So okay, we are proceeding in exactly the same way as we did in the previous example, except that we are using a different Möbius transform. Or a different conformal mapping. It was not a Möbius transform, but this is a Möbius transformation, which we have seen before. So in this case we are replacing set. We know the solution of this problem because we have alpha is equal to pi. It's 180 degrees, which is measured in radians. It's equal to pi. So instead of alpha we use pi, and instead of set we use W, and therefore the complex potential, which we denote F star, because that's not the potential we are looking for finally, and we use this expression and use the real part of this complex potential in order to find the solution of the potential problem. So it's easy for us using the formula I showed you. This formula where we know the alpha 2 and the phi 2 and phi 1, which are 3000 and minus 3000 respectively. We obtain this formula. Taking the real part of it, we obtain the potential function, and proceeding exactly as we did in the first example, we obtain that the complex potential in corresponding to the inner part of the circle, which we denote f of set, should be equal to this f star of f of set, where f of set is just the Möbius transform. And instead of using f of set, we also can use these variables u and v, and they are used when we are considering the the real part of this complex potential, which is the solution of our problem here. So now we find the solution of the potential inside this circle by just doing exactly as we did in the first example. We just write phi of xy equal to this phi star, where f star is defined here. And we know that this phi star is just 6,000 over pi multiplied with the principal argument of w. And we know that w is in fact this expression for the Möbius transform, 1 plus z over 1 minus z. So we have just inserted this expression into the formula for phi. So now we have the solution in this region. We can also express this set by x plus iy. Then we have a function of x and y as well. But we don't need to do it because it's nicer expression. Let's just have a short look about on the equipotential lines, for example, and the force of the power lines here. So we know that in the problem, the trivial problem that we have solved before, these equipotential lines, this green line, are just straight lines. So the temperature is constant on these straight lines, and these straight lines, due to the fact that we have a Möbius transform which maps this region to this region, we know that the Möbius transform is always transferring circles onto straight lines or circles in the UV plane. So we know that this straight line must correspond to some circle or straight line. In fact, we get half circles here as equipotential lines, and some of them correspond to the straight line here, which is going from this point to this point. Now we also can consider the power lines where this defined by the imaginary part equal to some constant, and they are just curves which are 90 degrees compared to the equipotential lines, and we have here from the trivial problem, we know that these power lines are just circles like this, and these circles correspond to circles or straight lines in the problem where we want to find the solution.